At first, the conversation around the future of air combat seemed totally straightforward. It felt completely normal to assume that advanced coding and artificial intelligence alone would rule the skies. Just put a smart computer in a drone, right? But as engineers pushed these concepts to their absolute limits, an invisible bottleneck was quietly threatening to ground the entire uncrewed revolution. And when the industry finally realized what it was, well, this changes everything. Welcome back to Air Flight Space, where we explore aviation events, air safety investigations, industry developments, and the stories shaping our skies. Today, we're taking a closer look at a story attracting major attention in aviation. For years, the headlines have been absolutely dominated by autonomous drones flying right alongside human pilots. It all appeared completely normal until a major physical reality hit the drawing board. You see, the future of air combat isn't just about writing advanced AI software. It's about how to physically power it. These advanced autonomous fighters need massive, unprecedented amounts of electricity. Not just fuel for thrust, but raw electrical power for the actual brains of the operation. To understand exactly what's at stake here, we have to look at collaborative combat aircraft, or CCAs. Basically, these are uncrewed platforms conceived to operate alongside manned fighters. They're the highly anticipated loyal wingmen. Just for some quick background, defense sectors globally are racing to build these right now. They're hoping to multiply their air force capabilities without risking human lives. But as we're about to see, giving these drones the capability to actually fight alongside humans, it requires a staggering amount of energy. Section 1. The massive power problem. We all know the concept, but what is actually happening inside the airframe of a CCA to cause this massive issue? The sheer density of the power drain here is literally staggering. We are talking about advanced computing processing millions of AI calculations every single second. Add to that high-powered radar systems sweeping the skies, intense electronic warfare suites actively jamming enemy signals, and constant, non-stop sensor operations. Running all of this at the exact same time creates an electrical demand that traditional off-the-shelf drone engines simply can't handle. But what happened next shocked aerospace engineers and defense analysts alike. They were faced with the seemingly impossible engineering paradox. How do you generate enough power for a high-tech drone wingman without weighing it down with massive, heavy generators? I mean, think about it. If you add too much weight to generate power, it ruins the aerodynamics and the range. The drone literally can't keep up with the manned fighter it's supposed to protect. It was a total gridlock. Keep watching, though, because the final detail explains exactly how this gridlock was broken. Section 2. Hanwha's 2029 Engine Solution. South Korea has aggressively stepped into this void to attack this hidden hurdle head-on. Enter Hanwha Aerospace and the Korea Aerospace Administration, or KASA. They aren't just building another jet engine. They're literally building a flying power plant. So the absolutely crucial metric here is 100 kilowatts. Hanwha is developing a 4,500-pound thrust turbofan engine. But the major reveal? This will be the very first engine developed in Korea to integrate a starter generator directly onto the engine shaft itself. By doing this, it completely bypasses those traditional heavy external generators and supplies up to 100 kilowatts of pure electrical power directly to those massive CCA power drains we just talked about. It is an incredibly elegant solution to a massive physical problem. And this brilliantly illustrates a huge shift in the aerospace industry's mindset. As a Hanwha official clearly stated, as global demand for CCA and unmanned platforms grows, propulsion will be central to fielding these systems at scale. It's no longer just about who has the best code, It's about who has the engine capable of actually keeping that code alive in a high-stakes dogfight. This program puts Hanwha in a totally unique position to deliver performance and affordability at a speed the market desperately needs right now. Wait. This next detail changes everything. While this high-bypass design engine is expected to be ready by 2029 for bleeding-edge military drones, it has a dual purpose. Hanwha notes that it will also be perfectly suitable for small business jets and commercial aircraft. Think about that for a second. By designing it for the intense rigors and extremely high electrical demands of a combat drone, they're inadvertently creating a highly efficient, power-dense engine that could totally revolutionize small commercial aviation too. Section 3. South Korea's drone ambitions. This 4,500-pound thrust engine is just one calculated piece of a much larger, highly funded puzzle. Backed by a massive investment of 750 billion Korean won, which is roughly 498 million US dollars. Just consider the sheer breadth of this engineering assault. Beyond the 4,500-pound CCA engine, Hanwha is concurrently developing a 5,500-pound low-bypass turbofan strictly for low-observable, or stealth, uncrewed aircraft. Then there's a 1,400 shaft horsepower turboprop for medium-altitude UAVs. And if that wasn't enough, they're pushing out a massive 10,000-pound thrust turbofan for dedicated stealth platforms. They aren't just building a single engine here. They're building a complete, specialized catalog for literally every altitude and mission profile. But the situation is far from over. The story gets even deeper when you compare their uncrewed ambitions to their manned fighter programs. While Hanwha is absolutely dominating the uncrewed propulsion space, they're also developing the indigenous power plant for the future Block 3 variant of the manned KF-21 fighter. They're simultaneously powering the human pilots and the autonomous wingmen that will fly right beside them. It's a fully closed-loop aerospace ecosystem happening entirely within South Korea's borders. Section 4. The Future Aerial Battlefield. So, how does this newly solved power problem actually integrate into an active military strategy? What defense analysts find truly remarkable here is how seamlessly South Korea has connected its defense industry. First, you have Hanwha Aerospace and KASA solving that critical power and engine bottleneck. Then you have Korean Air, who actually just delivered the first low US CCA platform to South Korea's defense agency for real-world testing. And finally, you have Korea Aerospace Industries, or KI, in which Hanwha notably owns a 5% stake, developing the autonomous AI pilot systems. The hardware, the airframe, and the brain are all being developed in total synergy. The aggressive pace of this rollout becomes terrifyingly clear when we look at the timeline. In 2025, Korean Air's lowest CCA is delivered for testing. By 2029, Hanwha's 4,500-pound engine with that 100-kilowatt integrated shaft generator is complete, and this perfectly aligns with the ultimate target, 2032. That's the year these collaborative combat aircraft could officially enter operational service. It's not some distant science fiction dream. It is a hard, budgeted deadline that is literally just a few years away. So, what can we actually learn from this story? It turns out the race for the future of air combat was never just about who could write the smartest AI. It was a hidden, high-stakes engineering war over electrical generation and thermal management. As Hanwha and South Korea successfully merge 100 kilowatts of electrical power generation directly into the turbofan shaft, they aren't just solving a math problem. They're unlocking the skies for AI wingmen. The bottleneck has been broken. Thanks for watching Airflight Space. If you found this video informative, leave a like, subscribe for more aviation investigations and stories. Share your thoughts below. I regularly read and interact with the community. See you in the next video.